Hi, this is part 2 of the chapter 29 homework preview, and so now I'm going to do those problems here in the second row, 22, 26, 28, 33 and 46, all of course taken from chapter 29, which is a magnetism. Let's get started with number 22. 22, you've got the following picture. You've got a couple of wires carrying currents, and you can tell already that this one here has the current coming up, like out of the page. These ones go into the page, so one of them we don't know what the current is. And then we have this loop that's thrown around it. Now this loop is of course going to be the loop to which you're going to apply Ampere's law, which literally means you take the line integral of the magnetic field along this path. So the technique of taking line integral is the same as in the last question. So here it would probably be a lot more complicated to actually work through, because this is not a straight line. The magnetic field is not going to be constant because it's created by this collection of wires carrying currents. They're not particularly nicely arranged in some symmetric setup or something like that. So it would be a very hard calculation to do if you try to do it analytically. But lucky for us, the calculation has been done. That's the setup here, pretending somebody worked out by one method or another what the answer to the path integral is. And in my case, I got a value here, 3.77 times 10 to the minus 6 Tesla meters, right? The unit's going to be magnetic field times distance. In fact, if you sum a bunch of them, doesn't change the units. Alright, so your value might be different, right? We're given this value, and so we don't have to work this out, right? Nowhere in this question do we actually have to work out a line integral. We're just given the answer. It's this. So using Ampere's law. Now, Ampere's law states that you will pick any loop you want, right? This is not there's not some wire here or something. This is just some imagined loop that we've drawn in the air. It's a bit like when in Gauss's law we got to pick our surface, our Gaussian surface. The surface wasn't really there. We often made it match some kind of existing surface, right? Or like match the symmetry at least. But the surface over which we took the surface integral in Gauss's law wasn't a physical surface or something, a mathematical thing we imagined it would help us do the calculation. Similarly here, right? This path here is just somebody drew this sort of line in the air and decided we're going to integrate around this. Now Ampere's law states that this line integral evaluated is going to be equal to mu naught times total current running through it. Now that means if those are the only three wires, if we had a different loop that went like this, say, right? As long as those same currents run through it, they sort of stick through it, right? They come out of it or go into it. The line integral along this loop will be the same. The line integral of this loop over here will be 0, right? Because there's no current on the inside. So this value is given. This value is a constant that you know, so we just have to figure out what this is. So you can use Ampere's law and the values you're given to work this out. But what is the current going through here? Well, the one thing you have to be careful about here is the fact that they go in different directions. So what we're going to get is I1, but then I2 goes the other way, right? I2 goes down, I3 goes down, but I2 goes up, so I'm going to subtract I2, and then plus I3. And that's the total current running through it. The important part here is the sign. I could have flipped it. I could have said that I'm going to define this one as positive, those ones as negative, which of course would ultimately give me the same answer for I3, except with a minus sign. That would just mean that the direction is opposite from what I thought. And so you can pick which direction you pick as up or down is kind of up to you. It's positive or negative, right? But you have to be consistent, and your final answer will accordingly be consistent, right? You're going to get the same answer no matter which way around you set it up. you solve for i3. And that's it. That's all there is to number 22. So here is number 26. I'm only going to do 26a. I'm going to leave the second scenario to you. The second one, I think, is actually the easier one. So I've got to think in 3D, right? It's kind of hard to draw vectors with their lines, and you're trying to figure out, if you draw a line, you don't know which plane it's in and what. But B is along the x-axis, and the velocity of my particle, and we're told it's a proton, right? The proton is right here. It's moving in this direction, kind of in the z and in the x and z direction, but not in the y direction, and at a 45-degree angle. So the force, right? Let's not get confused here. In the question so far, we were mostly worrying about charges creating magnetic fields. A charge moves, it creates a magnetic field. Okay. But what's also happening is that if you've got a charge that's moving and there is already a magnetic field there, maybe due to some other wires or charges or whatever, right? There's a magnetic field at the point where the charge is, then it's going to experience a magnetic force. Right? So it creates magnetic fields too, sure. When the other charges around it will feel that. But this one also feels the magnetic field that's right here, created by all the other charges in the vicinity. So, this force, the magnetic force, is given by this expression here. Right? If this is not familiar to you, watch the appropriate lecture video. So again, it's going to be a cross product between V and B. So the way I'm going to evaluate it this time, because I think it's easier in this case, is I'm going to take V, the magnitude of V, and that's given, right? They're given in the question what the actual values are here, so you can plug those in, times the sine of the angle between V and B. Now you can see immediately from the diagram, this is going to be 45, sine of 45 degrees. Right, you give them those values, it's a proton, so a charge, you can work out the magnitude really quite straightforwardly. But this one here, right, has direction because it's a vector. This one here is the scalar, so I've got to actually add the direction to it to make this true. Direction by right-hand rule, which is, always a fun little thing to do. So let's just try this. 1, 2, 3, right? First vector, second vector, resulting vector. So in this case, V goes this way. Now, at this point, I want to break my wrist. Let me turn this page a bit, just so I can actually do this. So V is this way. V is this way. Which way can I stick out the middle finger? It's perpendicular to both. I can't possibly move it up here. That would break my finger joint. So it's going to be down. The alternative, by the way, another way of doing this same thing, is if you just keep your hand like this, and you say this is like first vector, your fingers as a whole are the second vector, and then the third, the resulting one's like sticking out of your hand. Like you might have like a spike coming out of your hand. It's the same thing as doing this, right? 1, 2, 3, it's the same as 1, 2, and then upwards here. Different ways of doing the same thing. So let's do this. I just did it actually, so do it again. First vector is V. V is this way, so middle finger. The resulting vector is down. In this case, because V and B, right, are sort of like in the Z and X plane, it means my middle finger, if I imagine actually putting those right here, my force would stick out back into the Y direction. So you really have to engage your 3D thinking here. So if my force is going to be purple, then the force that you're going to experience is going to be in the Y direction, the positive Y direction, right? Perpendicular to both, but is it this way or in the opposite direction? Well, right-hand rule comes to the rescue and tells us it's going to be in that direction. So whatever magnitude you work out there, right, your final answer, F, is going to be 0 in the X direction, 0 in the Z direction, and in the middle, you put whatever you got there. Right, that's how you're going to write as a vector again in the end. And that's it. Now for part B, same thing. Actually here they're at 90 degrees to each other because they're both along an axis. So you should have an even easier time. I'm not worrying about any angle between the two. But I leave that to you. Alright, number 28. Now this is kind of a fun one. Let's read it. Radio astronomers detect electromagnetic radiation at 45 megahertz, so that's a frequency, from an interstellar gas cloud. They suspect this radiation is emitted by electrons spiraling in a magnetic field. What is the magnetic field strength inside the gas cloud? Okay, so I'm going to put the pieces together here. Like, this seems all very mysterious. Like, how would I know about electrons and gas clouds? Well, let's start at the beginning. Why would an electron spiral in a magnetic field? Here's my electron. And let's suppose at one point or another it is moving in this direction. Its velocity right now. Now, suppose there was a magnetic field, and let's just say the magnetic field points into the page, right? So it's sort of like this. Remember that is the symbol we're going to use for magnetic fields pointing into the page. Now I don't know, what caused it. Some astrophysical process creates these magnetic fields. Probably some kind of current that's going on there out there in space. Some violent process of magnificent scale that we can't possibly fathom, right? So the idea here. Okay, but this creates some magnetic field, and you want to figure out what is the strength of it. So what's that magnetic field going to do? Well, because the electron is moving in it, it's going to act a force, right, on this electron. So let's figure out which way that is. Okay, V cross B, right? Let's write it down again. We had in the last question, F is Q. In this case, Q is the electron, right? Let me write out as Q, V cross B. Let's not cut corners here, right? Okay. So V is this way, B is down. So the force is to the left, right? Wait, no, it's not, because it's a negatively charged particle. So that means that it's going to flip the direction of the force. The force here is going to be to the right. Right? So here, Q is negative because it's an electron, right? That will change direction. So actually for this particular question, it doesn't actually matter. So what's going to happen? Well, what's going to happen is that this electron is going to start changing direction, right? Those are 90 degrees, which means it's not speeding up or slowing down. The acceleration to the right is going to make it turn. And once it starts turning this way, the force will again be perpendicular, because now V has changed. V will go from here. A little bit later, it's going to be this way. But then the force is again going to be perpendicular. So you get this circular sort of path. Right, meant to be a perfect circle of some radius r. So make sure you understand this, right? When the electron is up here, it's going this way. Well, again, then the magnetic force is going to be, you use the right-hand rule there, and you find the force is going to be this way. And when the electron is down here going this way, the magnetic force is this way. But because it's always perpendicular to the direction that it's moving in, that's what the law says, magnetic fields don't speed up or slow down particles. It's not constant magnetic fields. They just change directions. Alright. So, we want to figure out what the magnetic field is. But what we are told is not R. That would be nice, wouldn't it? No, we're told the frequency. So what's happening here? This thing is spiraling. As it's spiraling, it of course creates its own magnetic field. In fact, there's a bit more going on here. But you can imagine if it goes around once, it will have created one full sort of cycle of magnetic field changing. Right? If it goes this way here, the other way here, that will change the magnetic field created because the direction has changed. So if it goes around once, that's one oscillation in the magnetic field that it creates. So when we So it circles with frequency f is 45 megahertz, which is of course 45,000 million, sorry, 45 million times per second. That's the megahertz. So 45 million times per second is going around. So what are the pieces then that we have to put together? So we have that the force is Q, that's the electron charge, we write E, times the speed of the thing times the field. Right. And the angle is between the velocity and this thing is 90. So I should say one more thing. It says spiraling, right? Spiraling. This is a circle. Why is it spiraling? Well, if you imagine, in addition to looking down on this electron here, imagine the electron also had an upwards component to its velocity like this, right? Then that velocity component would not get affected by that force. Like the force changes it this way. It sort of go like, it would kind of hard to draw. It would go like this and come up, 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 up. So like if you look at it from the side, this is like the top-down view. If you look at it from the side, you'd see it is something like this. Go up, 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 right? So we're looking down at it from the top in this picture. But the motion in the, let's call it the z direction, the direction coming out of the page, that you can't see, and that velocity component is not going to contribute to the magnetic force, because that is not a component that's perpendicular to the magnetic field. And it's also not going to change due to the force, so we can kind of ignore it, but that's why it's spiraling, because it, who says that the initial velocity is directly this direction, not at some sort of angle slightly upwards, if that makes sense. It would be coming towards us, going in circles, 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 like this. Okay, but we can ignore that for reasons I just explained. We're not just ignoring it, right? It actually does not affect our answer. Okay, so we want to find this thing here. We don't know this. Okay, we know this. Well, that's good. What else do I know? Well, I know that the force, right, is going to be equal to ma, which is also mv squared over r. Oh, that's nice, because circular motion, right? So, okay, so that means those two things are going to be equal to each other. So I'm going to have that m, and m is of course the mass of the object that's circling, which is the electron. M e v squared over r is e times v times b. We can simplify this a little bit, right? We cancel out one of the v's. I'll let you do that. But how do we relate that to the frequency? Well, v, the speed, is going to be the path traveled per time taken, is the circumference of a circuit per period. Call it, right? The time once around in periodic motion that repeats is called the period. So if it keeps going in a circle, time once around is the period. How does period relate to frequency? Well, t is 1 over f. Right? If you don't remember that, maybe you didn't really properly cover it ever, that's okay. Let's just think about simple examples. If it takes 1 second around, it's going to go around once per second. Frequency is 1 because it goes around once per second. It takes 1 second. If it goes round twice per second, it means it takes half a second to go round. 2, 1/2. If it goes around 10 times a second, f is 10. Well, then t is 1/10. It takes 1/10 of a second to go round. If it goes around 1,000,000 times a second, then so f is 1,000,000, then each cycle takes 1,000,000th of a second, right? So this relation is very intuitive. You just think of some numbers. So now we put all the pieces we need, because we're given this. So you can figure out this. So you can express your v in terms of the unknown r and in terms of t. Now, but you're like, but wait, I don't know r. What am I going to do? Well, do not fret. Help is at hand. Namely, if you actually plug this in, so let's do this, alright? We're going to cancel out this and this, right? The V over R. Now you plug this into here, it's the only V left. The R up here is going to cancel the R down there. So you don't actually ever have to know what the radius of it is, because that dependence will cancel out, and you can solve this thing for B just fine. It's funny that this problem is like a one bar problem in the textbook. I think it's a bit more complicated because you really have to like figure out what is it telling me, like how do I set this up. I think it's a lot harder than some of the other ones. Even if ultimately it's just an application of circular motion in a magnetic field, which you could argue is a sort of standard problem, right? Something that's also covered in the lecture videos. But there you go. So you know, make sure the pieces go together, make sure you understand what's going on here. Fun little problem, with real astrophysics applications. Okay, let's get going with the next one, number 33. Here we go. This is number 33. So the setup is this. We've got a wire. It's meant to be this little thing here in the middle. And the wire, we don't know the length of it, right? But we do know that the whole thin wire weighs 2 grams. Presumably, if it has a current through it, like it's connected to something else over here and here, it actually forms part of a circuit, but that's not a part we care about right now. So a 2 gram wire, now if you just hang this wire there, you let go, it's going to fall, right? Why is it going to fall? Because of gravity. Now, our goal is to use magnetic forces to levitate this wire. So if I draw a free body diagram for this, let me do it in a little corner over here. I've got a weight that's down, right? Weight mg, and I better cancel that with a magnetic force F mag. Right, so magnetic force to cancel out the weight of the wire so that it levitates and it doesn't fall. So the current in this case is fixed. I need to figure out what is the direction of the magnetic field. So I want the force to be up. The current is to the left, and so you can already think of given what you've worked through so far, you're like, wait, it probably means the magnetic field is like in the third direction, so not this way, not this way, but like either into the page or out of the page. So which is it? So the force on the wire, right, is given by this. The current, and I sort of think of the current as the vector because the current has direction, but some people write the length of the wire as a vector, like it starts here, goes to here. It's fine, right? It gives you the same thing. The current goes this way, so that is my vector. So in this case, we're kind of applying the right hand rule like backwards, like we know the answer, and we want to find the second vector. Now, how do you do that? Well, let's be honest, it's a 50-50, right? It's either this way or out, so let's just go with one and see if it works, rather than trying to have some kind of backwards right-hand rule to figure out, like if you're normally given this and this, I can work out this, but what if I'm given this and this? Just try, there are only 2 options, right? So, here we go. If the current's to the left, the magnetic field points into the page like this, alright, thumb to the left, magnetic field down, then my middle finger, my fourth finger points down, that's wrong, which means, since I can't change direction of current, I'm going the other way around, like this, current to the left. If the field comes out of the page like this, and make sure you do it with your own hand, not with mine, that means my middle finger, if I can't possibly bend this way without breaking the finger joint, the force will be up. So that means I want the magnetic field to come out of the page like this. Right? I mean, I don't really care what happens up there and down here. Really, where the wire is needs to come out of the page. And the strength of it, well, that's easy, because you know the weight. That has to be equal to the magnetic force. The length of the wire, now we don't know the length of the wire, but what it does tell us is that that length where there is magnetic field is, in my case, it's 10 centimeters. And of course, when I put L in here, I only count the area where there's magnetic field, right? I don't care how much longer the wire is out here. it's not going to change the magnetic force on it. So the L is going to be 10 centimeters in this case. The current is given, the magnetic field you work out, the force better be equal to the weight. And that's it. Not much to do here. So here's the setup for number 46. We've got a complete loop, right? A complete current loop. Of course, to actually make this work, I might imagine there's a little battery somewhere, you know, sort of off to the side, like here. And the wire has some resistance, so I get a finite current, right? But we're going to get this setup where there's the current flowing through this loop, and it's 5 amps. We want to find the magnetic field here. Now, at this point, you're like, I have no clue how to do this. Right, this is like, okay, this is like a funny shape. Like, where to even start? All right, let's split it up. The one thing we're going to need in terms of math is that the magnetic field, the center of a loop, is given by this expression. Sometimes you see that like N at the top. That is if you've got multiple windings. Actually, let me put an N in the top here, right? If you've got multiple windings, we call it a coil. But in just one loop, that's just one, so that's why I did write it at first. So R here is the radius of the loop. But this is not a circular loop, is it now? Well, it's gonna be fine. We're gonna use that, and let's make sense of this setup here. So I think you agree with me that it's probably sensible to split this up into 4 different segments. There's this segment here, and this segment here, the straight bits that point straight towards the point or away from the point. I want to color those in the same color because the same logic is going to apply to them. Then I'm going to have this thing here, and then there's the outer loop, which I guess I'm gonna go with red here. All right, this is like the outer loop here. All right. Each one of those segments may or may not contribute to the magnetic field at the point down in the center here, right? So these points here, this is a current that points straight towards this. This is a current that points straight away from it. So B to the straight segments, what's that? Well, if you if you imagine a little particle here, a moving particle, right? The point is in the same direction that you're moving. They're parallel. Your R is parallel to your V. You're not going to create any magnetic field at all over there, right? A magnetic field is created left and right around the wire, not in front of it. 0. So it's really applying. You can think of it as applying the Biot-Savart rule here. Like you say, okay, this tiny bit of charge is moving this way. So the velocity is to the right. The point connecting where the charge is to where I want to find the field is to the right. So they're parallel. So those charges moving in here don't do anything. Same logic here. They're moving straight away from that point here. They don't contribute any magnetic field there. They'll have a magnetic field here and here, right next to it, sure, but not right behind or right in front. So we only have to worry about the remaining 2 parts of this. So let's call this the inner loop and the outer. The inner loop is half a loop, right? So this one here, we're going to get B due to the inner, so the inner segment of the wire. Well, what shape is this? It's half a loop. B center of loop for, we write it like this, for half a loop. It's going to be mu naught over 2 times the current, 5 amps, times N. In a sense here, so I'm going to put my 1/2, right? It's half a turn divided by the radius, which is, of course, 1 centimeter. The current is 5 amps. And the same thing applies to the outer loop. The outer. This part here, right, creates a magnetic field in the center of it being half a loop. So, same thing. write out again. Mu naught over 2 I times, it's half a loop. No, R here is actually 2 centimeters. So it's going to give you a different answer. Now, I just add them, right? Yes, sort of. We have to be careful about the directions. Which direction is of magnetic field is going to get created here. So let's look at the green one. So one way you can do this is you take in your curly hand, right? And I move along it, and I pick, like, okay, for this part here, this piece of the wire where the inner loop starts, my fingers point down if my thumb is in the direction of the current. When I'm over here, right, my thumb in the direction of the current, again my fingers point down. So in this case, the B field is going to point down by the curly hand rule, or you could imagine you have a charge moving along here and you use the Biot-Savart rule. They're going to get everything's going to get you the same answer. Right? Down by I'm going to write the curly right hand rule. And similarly, because this goes the other way, right? So if I move along here with my current, then on this side here, as I move along, where this point is, my finger is always pointing up. This is up by the curly right hand rule. So if I add them, I have to actually subtract them, right? Now this one's going to be bigger than this one. Like the green wire does more than the red one, probably because it's way closer, right? The R is different. So I'm going to take this minus this, and the green one wins. So overall the field's going to be down, but it's the magnitude is this minus this. There's a trick here that if you feel awkward about moving your finger like along the wire, and noticing that your other fingers are always sticking up where this point is, a trick you can do is you can flip it. That I'm going to have my fingers, like for current loops essentially that works. If I have my fingers now go along the current, remember before the fingers were the magnetic field. But if I now switch it, that my fingers, I align them with the current, then my thumb is going to tell me the direction of the magnetic field. So for the red one, my fingers point this way, the magnetic field points up. Set down here. For the green one, to curl it along the direction of the current, my fingers point in the direction of the current. Do it this way, the finger pointing down. So this is how we got down, right? But that's equivalent to doing it the normal way, where I'm saying my thumb is the direction of the current. It's just as I have to move it like this, and every time it points up where the point is. But so this trick of flipping it is just another thing that you might be like, hey, no, that's crazy. Why are you confusing me with more hand rules? Or you might say that's the easiest thing ever, right? It's up to you if you wanna use that or not. Okay, that concludes the second part of this homework preview series. In the third part, I'm going to go through numbers 59, 75, and 79. I'll see you there.